Okay, no. Okay. So, yeah, so for this lesson, I wanted to go more in depth with the different types of robot mechanisms, just so all of you kind of get an idea of how to essentially design a robot for FTC. I don't care if you're a programmer or a CADer or a builder. I think this is good information that everyone should know. So, yeah. So first off, I'm going to start with the drive trains. So there's different types. There's 6. There could be others that I don't know about. But those are probably going to be like more unique, more kind of like interesting, kind of weird. But these are pretty basic. These are most people use either one of these. So on this side we have basic drivetrains. So basically this means that the robot can only rotate left and right, kind of like a car a little bit. So there's different types of this. So there's a robot with only 4 wheels, pretty basic, and there's a center drop, which I'll get into when we get there, and there's a tank tread, so it literally looks like a tank. So yeah. So, and on the right over here we have holonomic. And so holonomic drive basically means that you can actually strafe left and right. So you can literally move like left and right, kind of like in a video game, like just walking sideways basically. You could also drive diagonally. So instead of having to turn your entire robot left and right, you could just move left and right. So there are different types of this. So we'll go into the Omni-Wheel Drive, the Mechanum Drive, and the Swerve Drive. So first things first, we have the Fourwheel Drive. It's pretty basic, self-explanatory. You have 2 stealth wheels in the back. These are called stealth wheels. They're just basic wheels. I don't know what else to tell you. And you have 2 Omni wheels in the front. So Omni wheels have these little rollers, the little black dots around. This lets it kind of slide better. So the reason why there are Omni wheels in the front is it basically makes your turning like more smooth. Because if you just had 2 stealth wheels, turning could sometimes skip, or your robot will kind of like vibrate, or like it just kind of gets funky when you don't have when you don't have rollers on one of the on the front wheels. It's also an option to have like fully Omni wheels in the back as well. That just makes turning even more smoother. However, that could allow for you to be pushed around by other robots. So sometimes that can get annoying. If some robot is playing defense and they accidentally run into you, you'll get moved. So yeah, I guess I kind of explained the pros and the cons already. But yeah. Oh, okay. Okay, so yeah, this type of drivetrain can be powered with 2 motors using chain. So usually you would have like a motor in the middle with chain connecting to the wheels. But most of the time it's just like, 4 motors directly attached to these wheels, which is yeah, fine. Yeah, like I said before, the turns are still kind of not as smooth if you don't have all Omni. So yeah, pretty basic, not much to say with this one. So yeah. Okay, so this is the center drop drive. So this one's kind of interesting. It has 6 wheels, as you can see. However, it's very slight, but the middle wheel is positioned kind of lower than these 2. And the reason for this is, like as I stated before with the 4-wheel drive, turning it'll skip and like vibrate, and your robot will shake a little if you turn. This reduces that, since the wheel in contact with the ground is the center one, and these are kind of freely moving, so you won't really run into that issue. It's kind of hard to explain. I wish I could show you guys, but yeah, that's basically the plus with this. Oh yeah, and you get more grip with the ground. So if you have an Omni drive, the wheels with the stealth wheels are rubbery, so they stick to the ground better. These slip around, and so if your wheels are spinning very fast, they're not going to have traction with the ground. So sometimes your wheel will just spin without actually moving the robot because the wheels are slippery. So with this design, all of your wheels have grip with the ground. So you could probably go faster with this one. So some cons is that, well, yeah, obviously you can't strafe. So we'll get into holonomic later. But chain is actually required for this because you need to connect all 3 wheels to each other. And chain is just kind of annoying to work with. It's literally like, it's made of metal and you have to like dig your fingernails into it to like get them unlinked, and then you have to link them. And it's just annoying to work with chain. But chain it has its benefits, it's just really hard to work with. Also another con is that because this wheel is like slightly lower, your robot's gonna be wobbling, kind of like a teeter-totter. It's very slight, but yeah, that's just a little thing to look out for with this drive. So yeah, this is also pretty basic, and yeah, that's it about that. So now we're onto the tank drive. Pretty self-explanatory. There's no wheels, it's just tank. This is called tank tread. And the reason why you would have this drivetrain is if there's an obstacle in the game, or like you have to go over like a ramp or something. You know, there's bumps on the field. This will get you over those. Yeah, you could also, it only uses 2 motors. So this little sprocket right here is connected to a motor, and that's what drives it. The cons to this is it's actually very slow. Simply because you can only use 2 motors for it, and 2 motors is like not really the best option because that literally makes you slower. You're not powerful. And you need to tension the tread properly. So that's what these little white spools on the bottom are for, is for tension. So if your tread is too loose, that's not good. It might slip off. If it's too like tight, there's too much tension in the drive, and it's not bad. It needs to be, you need to have like a perfect balance between like looseness and tension. So it takes a while to kind of adjust how long you need your tank tread to be. So it's kind of like the chain issue. You constantly have to adjust it to make sure it's just the right length. But yeah. This drivetrain is not popular. Most people don't use it, and I don't recommend you to use it. I'm just letting you know that it exists, but it's just not like, it's not ideal for competition, okay? Mostly because it's slow, okay? In FTC, everything is about speed, speed, speed. You don't want to be slow. So yeah, I'm just saying I don't recommend this at all. But yeah, here you go. It's out there, you know it exists. So yeah. Now we're moving on to the holonomic drives, and this is where things get a little more complex. But there's a lot of benefits with holonomic drives. As I said before, you could strafe left and right and move diagonally. So this is called an omni-wheel drive. However, there are 2 types. This is called an H drive. So as you can see in this picture right here, there are omni-wheels in the middle, and they're connected to a motor. So this allows the motor to spin those wheels so that you can move sideways. Also keep in mind, the main wheels for the drive are also omni. This is a requirement in order to be able to go left and right, because the rollers will roll you that way. Yeah, there you go. So the cons with this one is you can't move diagonally. All you can do is move left and right, forward, backwards, which is fine. Diagonal movements aren't really, like, you don't really need to do them, so that's fine, I guess. However, you need to use an extra motor for this like center thing, so that might be an issue. It takes up a 5th motor. In this picture, they're using 2 motors for the drivetrain, but ideally you would still want to use 4 to get as much power as possible. So yeah, usually you're taking up an extra motor for with this drivetrain. Also, strafing is slower because literally it's using one motor to power the left and right movement, so strafing is like super slow compared to your normal driving forwards and backwards. Yeah, so that's all I have for this one. So now we're gonna go into the X drive. So this one's kind of funky. Um, it looks very weird. So your wheels, they're Omni wheels, are kind of in an X pattern. So like pointer. So yeah, they're kind of like diagonal. Yeah, this one's kind of fun. This one's actually more common than this. Okay, I see this a lot more. Yeah, the cons to this one is that it's a weird shape to kind of work around. Like, it's kind of odd how your wheels are like diagonal when usually they should be like straight facing. So I think it's just kind of a hassle to work your design around it. Also, there's a weight with this robot. Your weight has to be as centered as possible, or else if your weight is too much on the left, then you're going to start drifting to the left. So yeah, you have to keep that in mind. You need your weight to be as centered as possible with this robot, or else your driving is going to be out of whack, and you don't want that. You want to be able to drive straight when you want to drive straight. 4 motors are needed. I don't know why I put this in cons. I mean, most of the time you're going to use 4 motors. I mean, it would be nice to not use that many, because you only have 8. Yeah, you need 4 motors for this. Yeah, that. Oh, okay. This kind of this diagram up top explains how it works. So this is for my programmers out there who need to understand how the motors need to rotate in order to make this thing move the way it should. So to go forward, the front wheels have to go, like the arrows show you which direction the wheels have to rotate in. So yeah, to go forward, these rotate inwards, and the back rotates outwards. And it's literally the same idea, it's just rotated to go left, so these go inwards, these go outwards. And to go diagonally, you just power these two on the corners. Same thing for the going diagonally right or left. You would power these two. Yeah, pretty simple. Okay, yeah, that's all I have for this for this drivetrain. Okay, so now we have Mechanum. Everybody loves Mechanum. You're gonna see Mechanum a lot. Okay, most likely we're all going to be using Mechanum. We have Mechanum wheels at school, enough for all of our teams actually. And when you're at competition, you're gonna see everyone using Mechanum wheels. Okay, Mechanum wheels are just superior. Okay, this is like there's no question about it. Most of the time we would use Mechanum wheels. Yeah. So the thing with Mechanum wheels is that just like the previous X drive, you need 4 motors to power each wheel individually. Yeah, obviously it also strafes side to side, and it could also move diagonally. Yeah, so the magic with these is that these wheels are shaped in a way that the rollers are angled. Also keep in mind that there's a different wheel for the left and the right side. Like, these are not all the same. So this wheel is not the same as this wheel. They're like mirrored to each other. So yeah, there's a difference there. Yeah, like I said, they strafe. Yeah. This is I think these are better because it's simple, right? You don't have to like deal with this monstrosity. Like, it's just in the like corner. That's so weird. Okay, this is normal. Your wheels are just on the sides. Okay, there's nothing to worry about. Actually, yeah, this one's faster than Omni, simply because the Mechanum wheels, the rollers have more grip. Like I said before, the more grip you have on the field, the faster you like move, because your wheels aren't slipping. So yeah, this drive has slippage because of these wheels, just because of the type of wheels. Yeah, so these are grippier. The only cons is that these wheels are actually very wide. They're like 2 inches thick. So yeah, you just have to keep that in mind when you're designing your robot, because you have to fit within that 18 by 18 by 18 square or cube. So being too wide is something to look out for. So yeah. Also, your weight also needs to be centered on this, or else your robot's gonna get thrown off. It won't drive as straight as you want it to. However, I don't think it's as strict compared to the X Drive. Like, I think you have more leeway with the way your weight is distributed. So it's not as severe in a sense. So yeah. Mechanum is superior. Most of us should be using Mechanum. So yeah, that's about it for Mechanum. So now we're going into Swerve Drive. Swerve Drive is very interesting. So yeah, I call it like shopping cart because the wheels are like what's it called? They're like swivel wheels, and shopping carts have like swivel wheels. I don't know. So yeah. So basically, the way a Swerve Drive works is that the individual wheels themselves spin around. So this picture here shows the mechanism. So it's actually like very complex. At Heritage, none of us has like tried to make this. It's very complex. It requires like four servos and four motors to make, and you just need to be pretty good at designing. And everything on this is custom made. Okay, we can't make this with Tetrix parts like purely. That's not possible. So yeah, it's hard. It's not. I don't recommend doing it if you're a beginner. So the reason why you would make a Swerve Drive is because the mobility is actually better than the Mechanum wheels and everything else. Because you could strafe, you could go diagonally. In fact, you can move at any angle really, because the wheels are spinning freely. So yeah, you can move in literally any direction. You could also be spinning while moving, which is pretty cool. Yeah, you also have better grip with the ground because Mechanum wheels, although they do have like better grip than Omni, there's still rollers on it, so their grip is not as good. This is just a normal plain old wheel, so your grip on the ground is going to be better. So yeah, it's cool. Yeah, it's bulky too. It's very tall, as you can see, and it takes up a lot of space on the sides here. So it might be kind of awkward to work with as well. This is not very common. I think the really good teams know how to pull this off very well. I don't recommend that we try it. It's kind of scary to try to pull this off. Yeah, I don't know. It's very cool, very epic, but I don't recommend it. Mechanum is still king. Yeah, you're still gonna see Mechanum wheels most of the time. I actually have not seen a Swerve Drive in real life. I've never seen anyone we're competing against. I've never seen anyone have a Swerve Drive in real life, so I don't know. I don't really worry about it too much. It's just here you go. You know that it exists. Only the God teams do this. So yeah. Alright, so now we're done with drivetrains. Now we're going to go into linear motion. So linear motion is actually very important. You're going to need linear motion in every game because you're usually always lifting something every year. You have to lift something upwards, you need to stack something, you got to move something up usually. So there's different ways to do this. So there's linear slides, rack and pinion, linear actuators, scissor lifts, and the double reverse 4-bar. So I'm going to go into linear slides first. So this is what we usually use every year. We have a ton of drawer slides. We use drawer slides. There's different types as well, but this is just what we have as a club. We use drawer slides. So basically how it works is that I have this diagram here. So there's strings, there's pulleys attached to the sides of the drawer slides, and the string is just strung like this. And then when you pull it up, it pulls everything up. It's kind of hard to explain or visualize. I have this GIF here. It's kind of hard to see, but I think if you actually physically build it, you'll understand. So yeah, it's pretty simple actually. So the cool thing about this is that you could stack as many drawer slides as you want. So I could add more layers and layers of drawer slides to go even higher. Like this robot on the side here is probably using like, I don't know, maybe like 3 or 4, because it's like really tall. So yeah, and it's pretty compact too. The only con I have with this is that strings do sometimes slip off. So if your pulleys aren't designed in a way that keeps the strings in very well, if your string slips off, you're done for. It's dead. So yeah. Also, drawer slides are pretty heavy, but like I said, there's other types of slides that are smaller. They're different sizes and stuff like that that make it lighter. But drawer slides are they're heavy. If you actually felt one in real life, they're pretty hefty. But yeah, I don't. Yeah, that's it. All right, rack and pinion. Rack and pinion is interesting. It's kind of slept on. I don't see that many people using it, but I think it's pretty great. So basically, how it works is that there are these things called racks. So the rack is this like the thing that's going up and down. It's this thread, or not threaded. There's teeth on it. Someone said something in the chat. What? What do you want? Rack and pinion. Thank you, Antonio. Yes. Okay. So yeah, as I was saying, so there's teeth on this bar thingy, and this gear spins and it moves the bar up. So of course the bar has to be secured in a way. So this bar is kind of like sandwiched in between these other bars so that it kind of stays in. So yeah, once you see it, it's pretty basic. Yeah, you get the idea. So with rack and pinion, this isn't really used for like going really high up or anything. It's just a simple up and down motion, or you could also be side to side. Why am I lagging? Okay. Yeah, you could also do this horizontally or vertically. It doesn't matter. Also, yeah, like I said, you can't stack them up to go higher. It's just this one individual thing, and that's as tall as you go. However, your height depends on how long the rack is. So that might be a good thing or a bad thing. Basically, it kind of doubles its height, and that's all you have. So yeah, rack and pinion. Okay, next. Linear actuators. So these are also kind of interesting. It's similar to rack and pinion because it basically only doubles its size, and you can't stack them to go any higher than its original length. So yeah, it's just another way to go up or move horizontally, or maybe push something. So the difference between the rack and pinion and the linear actuator is that there's a lot of torque. Like it could lift things that are very, very heavy simply because of the way the screw design works. So because with the rack and pinion, if the thing you're trying to lift is way too heavy, the gears will grind or slip up because it just can't handle it. Oh, also I forgot to mention, in rack and pinion, the racks that we actually have at school are made of plastic, so yeah, they can break. So you don't want to be lifting things that are very heavy. Last year, or not last year, 2 years ago, we used a rack and pinion system because the game last year, you had to lift your entire robot up, and we used it last year. It was kind of sketchy. It worked, but it was kind of sketchy. It could have broken like at any moment if we kept doing it. So yeah, it's kind of, yeah, don't use it to lift heavy things. It's kind of whack. But the linear actuator, on the other hand, it's capable of doing that. So the way it works, think of like a glue stick. Have y'all like ever like ran out of glue on the glue stick, and you like make it go all the way up, and then you pull like the thing out, and then you'll see that it's threaded. The little hub is threaded on the inside, and it's basically just a screw. And so the carriage is actually guided with like, okay, this is actually fully enclosed, so it's guided by that. Yeah, that's basically just how it works. This picture right here is actually a legal kit that you can buy. So we're not allowed to use these. These actually exist. They actually look like this, except this is like X-ray vision. But yeah, we're not allowed to use these, but we're allowed to use these, and you could just buy them. So yeah, that's about it for the linear actuator. Okay, now we're on to the scissor lift. The scissor lift is kind of eh. I mean, I've never seen it in person either. I've heard alumni use it in the past and say they hated it, or scissor lifts are kind of like a joke. So like I said, I'm just letting you know that it's out there. I don't necessarily think it's the best thing. But yeah, this image kind of explains it. You also need to combine either the linear actuator thing or the rack and pinion mechanism to make the scissor lift. So to make this thing kind of go back and forth, you need to use those mechanisms to make it work. So yeah, the scissor lift can get really tall. However, it gets unstable as it gets taller because the scissors start to get closer together, so there's less support. It's also very slow because, oh yeah, I forgot to mention, linear actuators they're pretty slow, simply because there's a lot of torque. So torque means strength, essentially. So the stronger you are, the slower you are. The weaker you are, the faster you are. So kind of like that. It's slow rising. But yeah, this team was able to do it. I think they did it pretty well. This is okay. But yeah, scissor lifts. That's it. Double reverse 4-bar. Okay, I went over this last week, like briefly. But yeah, I'll go into more detail right now. So this one's actually kind of weird because I didn't comprehend it. It took me a while to comprehend the way it works because we actually attempted to do it last year with our robot. It didn't turn out too well, but that was our fault for not using the right materials. But I think this is there's a lot of benefits with it. Obviously, it actually gets really, really tall, and then it like kind of folds back down. So yeah, that's kind of cool. It's similar to the scissor lift, but not really. This is more stable. So how it works, I don't know if you'll understand because it took me a while to understand. But basically, there's no motors connected to the base. The motor is actually connected to the middle part where the gears are. You can't see it. It's on the other side. But basically, the motor just spins one of the gears, and this gear will spin that gear so that this goes up. And then this is where I struggled to understand. But as this gear on the bottom rotates, it generates a force that somehow like lifts up this like linkage over here. So it looks like it's defying gravity, but it's not. So yeah. Also, it's really blurry. But there's like rubber bands here. It relies on rubber bands to help it lift up. So yeah, rubber bands help it give it some more force to help lift it up and keep it up. So yeah, it's pretty cool. I don't know. I don't see this very often either in FTC. Like I said last week, it's used a lot in Vex. I think it'd be more interesting to see it. I mean, I don't think there's no way we're gonna use it this year. But you know, maybe in the future, this might be interesting to see sometime. So yeah. So now
I have a question.
Oh yeah, yeah.
On that, when it goes up, does it come back down, or can it stay up?
Oh yeah, it stays up. That's why I said that there are rubber bands. So the rubber bands help it stay up. Yeah, there's a lot of that. This is kind of like an issue with this mechanism. You need to have the right tension with the rubber bands, or else it'll be too weak to stay up. Because without the rubber bands, it'll just fall down. So yeah.
Okay, thank you.
Yeah. Okay, intake mechanisms. So every year there's something you need to be intaking. There's something you need to be like there's an object that you need to be manipulating. This year it's the rings and the wobble goal. So yeah, there's not that many. There's probably others that I don't know about that are too creative. But yeah. So now we're gonna go over claw grabbers, the wheel intake, rollers, and conveyor belts. So onto the claw grabber or gripper. This one's also kind of self-explanatory. The like GIF kind of explains it. There's one servo powering this whole thing, and then the gears kind of do all the work. So yeah. This is only good for picking up small things. You could probably scale it up to be really big to pick up a larger object, but it's still the same idea. Um, so I think I think this would be interesting to see, to pick up a wobble goal this year because there's like a pole on it, and this would be perfect to grab with it. So yeah, just a little tip, little inspiration. So yeah, that's it. Simple. Okay, wheel intakes. These are pretty epic. We see these are very common. We see these a lot, especially whenever the game requires you to grab blocks. So like this game, this was last year's game. So yeah, basically all it uses is two motors that spin the compliant wheels. These green wheels are different because they're squishy and they're kind of sticky. So they're good for gripping things and like sucking things in. So that's why we use these types of wheels. It looks like the flywheel design. We'll get into flywheels later. It's kind of like the same thing. So yeah, the cool thing about this intake is you could actually grab the block by the corner. So like I keep circling it, but yeah, right here it grabs it by the corner almost horizontally, and then it kind of reorientates it so that it fits. So it's very versatile when you're trying to grab things. So you don't need to spend time lining up at the right direction to pick up your block. All you gotta do is go up to it and it just sucks it in. So it's very efficient, very cool. Wheel intakes are pretty great. I don't think we're gonna use these this year. I don't know. People might, but we'll see. So yeah, okay, now we're gonna go into rollers. This is why I think rollers are actually good for this year. Literally, these are videos of people who made a robot for this game already. So yeah, the way it works is there's one spinning axle. This one has multiple. Yeah, it could be multiple to kind of guide it up. So yeah, and then usually there's either surgical tubing or the green compliant wheels on it. So like kind of like these wheels. However, there's a smaller version. So yeah, it's right here. So yeah, surgical tubing is, or I like to call them noodles. They look like noodles. It's these things. Yeah, they look like noodles. Yeah, sometimes it's adjustable. So what I mean by that, why am I lagging? My mouse is lagging. Okay. Yeah, so what I mean by adjustable is as this one intakes, you see it kind of goes up. There's an axle connecting it here, so you can kind of move it up and down. So that's what I mean by adjustable, so that it kind of hits the ground more, and then it adjusts itself back up to account for the space of the ring, I guess. So yeah, that's also a thing. Yeah, this is just me giving you guys ideas for this game. It seems like this design works better than this design. Just because I've seen more. You guys should watch Robot in 3 Days. You should just YouTube that, look it up. Robot in 3 Days Ultimate Goal. And people have already made robots for this year. And I see this type of intake more often, and it seems to work better than this. So yeah, just so you know. Maybe you should use this. Yeah, that's it. Okay, conveyor belts. So conveyor belts are interesting because you could also move things upwards. So in this video, they're moving the balls upwards. You could also move things horizontally or sideways, obviously. But yeah, conveyor belts, personally, I don't think they're the best intake. But I do think they're good for transporting things within your robot. So if you wanted to move, okay, so if you wanted to move the rings up, so this team is actually using a wheel to kind of guide it up, but you could also use, a conveyor belt to guide them up this long line. So, that's also an option. Cough, cough. I'm just giving you guys design tips or design ideas, pretty much. So yeah, there's not really much to say about conveyor belts. They just move things up using. Oh, this is using tank tread, by the way, just like the tank tread drivetrain. They use tank tread as a conveyor belt. Same thing, pretty much. So yeah, conveyor belts. All right, launching mechanisms. So kind of like what we're doing this year. There's only two. There's probably others. Like I said, there's probably other designs that I can't think of right now. These are just basic. So yeah, let's get into the flywheel. So the flywheel, like I said, is very similar to the wheel intake. The only difference is it's spinning really fast and it's outtaking instead of intaking. So if you can see in this GIF, it's like the same idea, right? There's two wheels on the sides and then they're just spinning. This is good for just shooting, literally just shooting any object, usually balls or rings. The thing about this design is that it shoots fairly straight. The catapult is different. I'll go into that later. But yeah, this shoots things pretty straightforward. So yeah. Also, this one is a more creative design of a flywheel. So this looks different because it's kind of curved. And then the flywheel is just in the center. Wow. The flywheel is just kind of right there. So you don't necessarily need two wheels. You could have one. So like for this example. Also, this is on a rotating turret, which is kind of complex. But yeah, the shooting mechanism spins with the robot, which is kind of cool. Yeah, just a little cool thing to look at. I like it. Anyways, yeah, that's pretty much it for flywheels. Pretty simple. Just two wheels spinning really fast and just shoots things. So yeah. Alright, catapult. So the catapult's kind of different, or it's very different. I think it takes up a lot more space, as you can see. It takes up almost this whole robot. So the way it works is that this is a spring, and it's creating tension, and then there's also a rope, and there's a motor somewhere below. So the motor is just kind of spinning the rope to bring this channel backwards, and then the motor kind of releases it, so it turns the other way to release, and then the spring is really doing all the work here. It just kind of pops it back forward or something. Yeah. That's just how it works. Catapults are best for shooting balls. I don't think using a catapult for shooting rings sounds like a good idea. That's just me though. Okay, yeah, so the difference I wanted to show you guys was that the way the catapult shoots things is kind of like a parabola. So any of you in Algebra 2 know what a parabola is, but basically this picture shows it. It's kind of like a curve. Parabola. It's like an upside down parabola. So it curves, it goes up, and then it goes down. So this is different from the flywheel, because the flywheel just shoots straight up, straight. So yeah, this is why I wouldn't recommend the catapult for this year, because you need to shoot it straight into here. You're not really, shooting it up. You don't need to shoot it up. Wow, why am I lagging? Okay. So yeah, catapults versus flywheels. Yeah, that's pretty much it for that. Alright, so this is where it gets a little more technical. I've said the word servo before, but I'd like to explain that there's a difference between a motor and a servo. So a motor is obviously, it's bigger and it's stronger. We use different types of motors. So we use the Nevris. There's a Nevris 60, a Nevris 40, and a Nevris 20. These are all from the same brand called AndyMark. So basically the numbers mean the speed. So the 60, so the bigger the number, the more torque, so the stronger the motor is. But like I said before, the more stronger you are, the slower you are. So this motor is going to be slow, but strong. Wait, what? Oh. Okay. My phone rang. Okay. So the 60 is the strongest, the 40 is kind of like the mid-range, and then the 20 is like super fast. So yeah, just so you know that. Oh, also there's the Torquenado. The Torquenado is from a different brand called Tetrix or Pitsco. They changed their name. We call it Tetrix. So the Torquenado is a lot like the 60. It's essentially the same thing. However, the Torquenado has a stall torque of 700 ounces per inch, and the Nevra 60 has a stall torque of 525 ounces per inch. Well, what does that mean? What does stall torque mean? So what stall torque means is that it takes more work, or it's harder to spin the motor when it's unpowered. Like some of these motors, I could spin like the shaft with my finger. I could just like spin it easily. With the Torquenado, I literally can't spin it. So basically what this means is that it could carry more weight without its the motor turning and slipping. Like things won't slip down as the motor isn't powered. So this can carry more weight when it's not powered, if that makes sense. Like it won't turn the motor when there's a weight applied to it. I don't know. Did that make sense? You'll see when you actually start building and using it. You'll notice. So now I'll get into servos. So there's different types of servos. There's a 90 degree, 180 degree, and 360 degree. So servos are interesting because they're kind of like nothing like a motor. So servos rotate. They have a limit to how far they can rotate. So this one can only do rotate 90 degrees. This can rotate 180. This is 360, and that's it. It stops. It doesn't actually completely do full rotations like all the time. It only rotates to a certain degree. So this is handy when you're trying to when you're programming, and you want the servo to move a specific angle or something. You literally just tell you just program it to turn 90 degrees, 180 degrees, 45 degrees, whatever degrees you need, and it'll just go to that degree, and you don't really need to think about it. It's pretty cool like that. There is also a continuous servo. So a continuous servo is literally, it works the same way a motor does. It looks like a servo. It's still like a servo. It's weak, but it just rotates just fully like a motor does. However, the difference between a continuous and normal is you cannot specify your degree of rotation. It's literally like a motor. However, with motors, you can technically specify how much it rotates, but that uses encoders, and that's a programming thing. The programmers might talk about that after my presentation, so just so you know, encoders are important. But yeah, motors versus servos, that's all you need to know. Okay, gears. Okay, yeah. So there's actually different types of gears. So what most people think of is the basic ones like this. These are called spur gears. They're they're just normal gears that everyone knows about. Wow, the first thing you think of a gear is like that. So yeah, bevel. So now we're getting into the more interesting different types of gears. So bevel gears it's this one that I'm circling. So the cool thing about the bevel gears is that it changes the axis of rotation. So this one is rotating this way, but then it changes the rotation to this way. So that's kind of handy when you want to be compact with your design. In fact, I could show you why you would use a bevel gear. Why is it being laggy? Okay, whatever. Yes. I love this example. Yeah. So this is cool because, can I make it bigger? Yeah, okay. So the reason why you would use bevel gears is to kind of make your design more compact. So like motors are really big and they kind of are bulky. So usually your motor would actually be sticking out like in the middle of your robot. But in this case, they used a bevel gear to rotate the direction, or to rotate like the axis of the rotation, if that makes sense. So yeah, so instead of your motor sticking out horizontally, they were able to fit the motor on the sides over here, and then the bevel gear kind of changes the rotation to actually be the correct rotation for a wheel. So yeah, that's pretty cool. That's pretty much the only reason why you would use a bevel gear. So yeah, bevel gears are epic. Okay, worm gears. Now worm gears are a lot like the bevel gear. It does the same thing. The axis of rotation is, switched. So however, there's a difference. So actually, it can lock. So what locking means is that the output gear doesn't spin. So this video actually like shows it happening. He's trying to spin this one, but it doesn't work. He can't spin it. So that's kind of interesting for maybe if you need to lift something really heavy and you don't want your motor, you don't want it to slip back down, then this physically will stop that like slippage. You can't. So yeah, you can only go up and down and it'll stop. Like it'll literally stop. You can't slide back down because of the weight. So yeah. Oh yeah. So like I said, it's good for lifting heavy things. High torque. Torque means strength. So yeah. Helical gears. I've never seen helical gears in FTC. I don't think there are any like made for our robots, but I just wanted to go over it because it's kind of good to know. So helical gears look a lot like spur gears, except the teeth are angled. So basically what this allows for is reduced noise. So gears are really loud. So if you're actually at a competition, you're going to be hearing the gears. You're hearing the spinning. You're hearing the burr. Haha, robot go burr. So yeah, gears are loud. Also, it can handle heavier loads. So your gears are less likely to grind simply because of the angle they're connected. So they have more, I guess, literally there's more surface, they're touching more. So they're less likely to skip teeth or grind. If that makes sense. I don't know. It doesn't really matter. We don't really have helical gears, but yeah, just so you know. Helical gears are cool. Okay, gear ratios. So the reason why you would use gears is to gain an advantage. So if you want to gear for speed, you would gear for speed. If you want to gear for torque, you would gear for torque. Okay, most of the time you're not going to be using the motor directly. You're going to attach a gear to the motor to give the motor more power in a way that you want. So obviously gears rotate in opposite directions. So this one is rotating clockwise and this one's counterclockwise. That's just how it physically works. Yeah. Gear trains. So I'd like to mention that there's this thing called an idler gear. So what the idler gear basically does is it keeps your rotation, it keeps your output rotation the same rotation as the input. So these are both going counterclockwise. So A and C are both going counter. The idler just switches the direction for C. So yeah. Also, Having idler gears does not affect your gear ratio. So even no matter how many gears I put in between these two, your gear ratio stays the same. And I'll go over gear ratios after this.
I gear towards torque.
Okay, weird flex.
It's a pun.
Okay. I mean, yeah, you literally could. So, yeah. I think that's about it for the presentation. So now I'm gonna actually go into some math with the gear ratio so you fully understand. I already drew this out. I'm gonna just ignore that. We're gonna. I feel like a math teacher now. Ew. Okay. So basically, the equation for a gear ratio is gear ratio equals the output over the input. So what is the output and input? What even is that? So the output could either mean the amount of teeth or the diameter of your gear or the speed of your gear, so RPM. We don't really use RPM much in we don't really go in depth about with it in robotics. Usually all you need to know is that having a smaller input gear would result in having a smaller input gear and a bigger output gear would result in torque. Let me just draw that actually. Let me draw. So let's say, for example, this is your input and this big one is your output. The input basically means it's also known as the driver. All this means is that your motor is attached to this one. So let's say this has 10 teeth and this one has 20 teeth. So my gear ratio is the out, so that's 20 over the in. And this simplifies simple fractions into 2 over 1. So my gear ratio would also be 2 to 1. So what this means is that the input, so this gear rotates twice for every time the output rotates once. So technically your motor is doing less work to, because this will do a full rotation faster than the bigger one. So your motor is literally doing less work, which means that this will generate torque, which makes you stronger. You're essentially making the motor stronger than it actually is. However, you're sacrificing speed. Okay, you can't have both. You're either weak and fast or slow and strong. Okay. I could also switch it. So if I switch the roles here, I have my input a bigger gear and my output is a smaller gear. Still 20, 10. This is my input. This is my output. So yeah, so pretend the motor is attached to this one. So because there are more teeth, this one is going to lock onto those teeth, but because this one has less teeth and it has a smaller diameter, it will rotate faster. It takes less to rotate it, essentially. So I'll do the gear ratio again. So instead, the output is 10 and the input is 20, 1 to 2. So your ratio is 1 to 2. So what this means is that your motor this has to rotate once for this one to rotate twice. So it's 2 times as fast. So your motor only has to rotate this thing once for this to rotate twice. So you're 2 times faster, essentially. So yeah, that's kind of the math behind gear ratios. If you take Santana's Engineering 2 class, he will go more in depth and you'll learn about this. So I kind of taught you beforehand. So yeah, kind of good to know. Usually we don't really think too much about the numbers. Like I said before, all that matters is that you understand that the smaller input would result in more torque, and then a bigger input would result in more speed. Yeah, that's the end of my presentation. Pretty basic stuff that I think everyone should know. Yeah, I'm done. Any questions? Nope. Okay, well, I guess the programmers can teach now.
Yes.
I'm coming for Santanas Job. Yes. The school should totally hire me. Oh, Santana's watching me. Uh-oh.
Oh.
Yeah.
Is he judging me? Did I say something wrong,
Totally.
Santana? What did I
Oh,
say
you're
something
good.
wrong?
No,
No, I'm
a lot of
right.
information that was thrown at them, but I think it's good.
Yeah, I know, it's a lot to take in. But yeah.
Yeah.
Okay, wait, is it present window or
Oh,
Chrome
wait, hold on,
tabs?
stop. Okay.
I think go with window. I feel like window is safer. Okay. Okay, are we good? Can everybody see this?
Yep.
Alright, and then record.